everyone, welcome to Algorithm Seminar. Today we're happy to have Ellis here to give a talk. He's an assistant professor in the Brown University Computer Science Department, interested in graph, online, and approximation algorithms, as well as metric embeddings. He completed his PhD at Carnegie Mellon and did a postdoc at ETH Zurich. Please welcome our speaker.
Okay, cool. Should I get started? Yeah. All right. Yeah. Thank you, everybody, for coming out to my talk virtually and otherwise. I'm going to be talking about a collaboration with a variety of people at a bunch of different institutions. This is a talk about Steiner trees, so I'm going to just start with what Steiner trees are. And in particular, I have to stick my clicker in. There we go. I'm going to start with like this story about this thing called universal Steiner trees that was told in the first paper that introduced these things. So there's this paper that came out maybe 15 years ago that told the following story. Like imagine that you're some server and you'd like to broadcast to some subset of clients, like maybe these clients. And they now like maybe sending this message a certain distance costs you a different amount. And in particular, what this means is that like sometimes you might want to send directly to a client like on the left here, but maybe by first sending to an intermediate node and then broadcasting from that intermediate node, you can like reduce the total amount of distance that these messages travel or maybe cost you pay or something like that. And again, by sending the intermediate nodes, we can then like reduce the total like length of the edges that we're sending things over. So this is like a very well-studied problem in algorithms and theoretical computer science. It's just called Steiner tree. Namely, here we imagine that we're just given some graph G with vertex at V and edges E. Our edges have weights, and we're also given some fixed root vertex, and we'll see why I'm going to be talking about the fixed root vertex for this talk. And then we imagine that we're given a subset of vertices that I'll call terminals, which always contain that root vertex. So an instance of Steiner tree might look something like this. So I have my root here. The blue nodes are all of my non-root terminals. And now my goal is to just find some subgraph of this graph which connects all the terminals. So for instance, this solution in blue is a feasible Steiner tree solution.
You're not really using R.
So far I'm not using R, and you'll see why I'm talking about R. So our goal in Steiner tree, now sort of consistent with the story that I told before, is just to minimize the total cost of all the edges in the Steiner tree. Okay, so this is like a very well-studied problem in algorithms. It models a lot of problems that people care about. Like if you look at, I don't know, any sort of like VLSI chip design conference, there'll probably be papers about Steiner trees. It models these kind of communication network and broadcast problems. It was one of Karp's original 21 NP-complete problems, so it's really one of these like original hard problems. And in particular, it's so-called APX hard. So unless certain standard complexity assumptions do not hold, we do not expect there to be, there's some constant, one plus epsilon, think like 1.01, below which we know we can't get an approximation algorithm with that approximation factor in polynomial time. Okay, so sort of the scope of study on Steiner tree is mostly approximation algorithms. So we want things that run in polynomial time, but return like reasonably good solutions. And there's a whole long series of works on this, and that'll be kind of the scope of today's talk. Like we're interested in approximation algorithms for Steiner tree. So that's Steiner tree. And now, like if we return to this original story that I told, the people that first got interested in this thing called universal Steiner trees said, hey, wait a second. The way that I think about broadcasting in a network is not like some set of clients arrive and I want to broadcast to that set, and then I want to just sort of like recompute this entire structure every time a new set of clients arrives. Like what we want to avoid is sort of like new client set shows up, compute an entirely new Steiner tree from scratch. New client set shows up, compute an entirely new Steiner tree from scratch, and so on. So sort of just like repeatedly computing new Steiner trees is bad. I mean, it's bad from a computation perspective because we have to solve or approximately solve Steiner tree every time we want to broadcast. It's bad from a space perspective. So if you imagine that each of these nodes is sort of storing some way of routing, given that you're trying to broadcast to some subset of clients, like the naive thing that you might do and that you almost certainly want to avoid is sort of like tell each node how to forward messages as a function of every possible subset of clients, namely terminals that might arrive. So we'd like something better than this. And what is the thing that's better than this? Well, it's this thing called a universal Steiner tree. So informally, the way I want you to think about universal Steiner tree is it's just like a single spanning tree of the graph that's a good approximation for every possible instance of Steiner tree. And I'll be more formal about this in a moment. So the rough picture here is like I'm given some graph with some root. And now I can sort of like heavily sparsify this graph to just a single spanning tree. And now when I want to understand things about Steiner trees on the original graph, I can somehow just look at this single spanning tree. And this is like a genuine subgraph of the original graph. So let me do this a little bit more formally. So what is universal Steiner tree? So an α-approximate universal Steiner tree, given some graph G and some root vertex R, is just some spanning tree of the original graph where, well, if you look at any subset of terminals, the cost of the optimal Steiner tree connecting those terminals in that spanning tree should be at most an alpha factor larger than the cost of the optimal Steiner tree connecting those terminals in the original graph. Okay, and notice that the cost of optimal Steiner trees connecting things in the universal Steiner tree, namely the spanning tree, is always greater than that of the original graph because you're only dropping edges and there's only sort of like more things you can't use in the spanning tree.
This is the definitions for trees, but I guess it could also work with any type of sparsifier, right? You may want to sparsify your graph into a graph on which it's easier to compute a Steiner tree, like a planar graph.
Yeah, for sure. And I mean, you can ask all sorts of other different sparsification questions. In some sense, I guess this is like the most aggressive sparsification you can hope for because the graph better be connected. And like, this is like a minimally,
Is the motivation that like you can computing Steiner tree on a tree is trivial, or?
That's part of the motivation. Yeah. So that's part of the motivation. I'll return to the motivation in a second. But yeah, I mean, computing a Steiner tree is trivial. Now, sort of the amount of space that each node has to store, if you're thinking of this as a routing structure, is trivial. I mean, all you have to know is like, is there a descendant of me in this tree that is one of my terminals? And just like route to whichever one of your children is an ancestor of that descendant, but child of you. Yeah. I'm going to pause on this definition for Raj for a second since he just walked in. So yeah, you made it for the most important definition.
I've seen this before.
You've seen this before?
Yeah, probably.
Oh, okay.
Talk or
The talk, right?
Yeah, okay. Maybe you're at my talk at Fox. All right.
Yeah.
Oh, well.
You don't remember me complimenting you on it?
No. Oh, yeah. Well, you can compliment me again. If you want.
I'll compliment you again. Well, you got to deliver as well. But...
Okay. Well, yeah, we'll see how my delivery is. So, okay, that's a universal Steiner tree. So in particular, if you look at any subset of terminals, say this blue subset, and then you think about how to sort of connect them in the original graph and how to connect them on the Steiner tree or on the universal Steiner tree, the optimal solution on the right here should not be that much more expensive than that on the left. And notice that there are sort of edges on the right or edges on the solution on the left that are not edges on the right. And so you have to do different things there. Okay. And I guess the other thing that's worth noticing here is that the optimal solution for a Steiner tree on the right is trivial. Like there's sort of a unique trivial to compute minimally edge connected graph which connects these terminals. It's sort of just like the obvious tree which connects the terminals on the universal Steiner tree. So just quickly playing with this definition for a moment, I said I was going to say something about this root. Namely, I claim that there's like some sense in which it's necessary to have this assumption about the root, like that there's always some root vertex, which is always in the Steiner tree if you want non-trivial approximations here. In particular, I could like modify my definition as follows, like just take out all the things that have anything to say about the root, and now ask you to maintain approximately the cost of a Steiner tree for every possible subset of terminals. I claim that this is impossible except with maybe like a trivial approximation factor of, say, n. And this is where I ask you all what that is. I don't know how hard it is for people to answer over Zoom, so maybe it's entirely on.
They can
Yeah, they can answer. Okay, so take a very simple graph.
I mean, just a path along that, or
Path is actually easy.
no, but I mean,
Circle.
it depends, right?
Yeah. Oh, that way.
Oh yeah. So maybe I understand the definition. Okay, but maybe you can.
Okay, well let's we'll see what goes wrong with a cycle, and that'll maybe help us understand the definition. So I claim that if we modify their definition this way, and there wasn't this root which is always here, the cycle would be a bad instance for universal Steiner tree. Namely, any claimed universal Steiner tree just leaves out some edge. I mean, up to symmetry and rotation, say it's like that edge. And now, if our goal is just to connect those two vertices, the universal Steiner tree has to go all the way around like this. Whereas in the optimal solution, the original graph could connect them directly. And here I'm imagining that all the edges have weight 1. So there's this gap between the universal Steiner tree is doing by a factor of n and that of the original graph by which can get a 1. Okay, so somehow this like root assumption is necessary. I mean, I guess follow-up question, what's a good universal Steiner tree for a cycle?
Just leave out there the edge furthest from the.
Exactly, yeah, so like leave out, okay, yeah, so if you want an approximation a little above n, you need this root assumption, so returning back. Now a good Steiner tree for this cycle just sort of like leaves out the edge, which is furthest from the root. And it's easy to verify that this will give you like a constant approximate universal Steiner tree for the cycle. Okay, so this root assumption is important. And yeah, again, now our solution is like easy, or it's like good. So let me just return to the original motivation. So what's the point of this object? Well, like if you imagine sort of client sets arrive over time and we're trying to repeatedly broadcast to them, it's now all of a sudden like trivial to recompute what the optimal or approximately optimal Steiner tree is when we restrict to this thing. So, okay, so I told this like little story about repeated broadcasts, and this was kind of the original story told about universal Steiner trees. The other thing that I think is worth noting, this is more of a philosophical point, but like the existence of good approximate universal Steiner trees tells you something about the intrinsic complexity of Steiner trees. Like somehow you can sparsify, or at least approximately sparsify the structure down of Steiner trees to just like that of a single tree. And now the last point here is sort of like a theory point, in the set universal Steiner trees generalize a lot of other well-studied versions of Steiner tree. So there's something called online Steiner tree, where kind of the terminals arrive one at a time and you have to like irrevocably decide what edges to add to connect them. Here we know log n approximations, and that's tight, so they're lower bounds of log n. There's some sort of funny generalization of that called oblivious Steiner tree, which again is simpler than universal Steiner trees, which I won't talk about. But if you were to like look at the existing work on this, you'd say like, well, we know polylogarithmic bounds for these simpler problems. Maybe we can hope for polylogarithmic bounds for universal Steiner trees. So what's actually known about universal Steiner trees? Here's my nice little plot. So just from the previous slide, we immediately inherit this lower bound from online Steiner tree, because universal Steiner trees generalize them and we have a lower bound there, okay? Now, on the upper bound side, the best thing we knew was a result from more than 10 years ago that basically said you can get this funny sublinear but super polylogarithmic factor. So you can get like a 2 to the root log n approximation guarantee for universal Steiner trees. And now, like I've drawn these things in like large fonts and close together, but if we're thinking about this in the context of approximation algorithms, you should really think of these two things as being very far apart. And achieving bounds, you know, in general in approximation algorithms of this form is much easier than of that form.
2005 paper did not give any upper bound, it was just a lower bound paper?
It gave an upper bound for a sort of simpler version of this problem where you're working the complete graph and edges form metric distances, yeah. But for this more general graph version, we didn't know anything. Okay, so what did we do? Well, we kind of like closed this big gap. In particular, we showed that there always exists, given some root vertex R, some efficiently computable universal Steiner tree with an approximation factor of log to the 7. Yeah. Right. Yeah, okay, good. So returning to the picture, I mean, like kind of the right answer for universal Steiner trees is somewhere in this like much smaller polylogarithmic gap. Now, the picture is actually much more complicated than this, and there are actually many more papers on this. So you can sort of like restrict the graph that you care about in all sorts of funny ways, and people have, and you can study like different kinds of universal Steiner trees for different settings. In fact, we gave some bounds for other special graph families in our paper in addition to arbitrary graphs. The only thing I wanted to point out about the existing picture is that I guess prior to our work, the best thing we knew for general graphs was a result for planar graphs that gave like a log to the 18, I mean, very large polylogarithm if your graph is planar. And so this like log to the 7 bound blows the previous planar result kind of out of the water. So, but like it's like, the point here is that the general picture is much more complicated, but all that I really want you all to remember from this is that we had a log n lower bound and a 2 to the root log n upper bound, and now we have a polylogarithmic. Okay. Are there any questions about this before I move on? Cool. So, all right, so I'm going to try and spend like the rest of this talk giving kind of a rough general overview of how one shows this. I mean, if I have time, which I probably won't, I can actually give like the entire proof in the talk. So it's something like very simple. The algorithm is like quite simple, which is nice, but probably won't have time to go into the details. But I'll at least give like a proof roadmap. So the general picture is as follows. We'd like to compute universal Steiner trees. the way we do that is we're going to leverage a known connection to an object that I'll describe momentarily. And this object is called a strong sparse partition hierarchy. And basically, this previous work that showed how to get 2 to the root log n approximate universal Steiner trees showed how you can get those if you can compute these like strong sparse partition hierarchies with parameters that are similar, like 2 to the square root log n. Okay, so our entire work is going to hinge on improving the quality of these strong sparse partition hierarchies. And how are we going to do that? Well, we're going to like use these tools that I'll talk about called dangling nets and this problem called cluster aggregation. So I want to start by talking about the middle part of this, namely these strong sparse partition hierarchies. And if I want to tell you all what a strong sparse partition hierarchy is, I first have to tell you what sort of like a single strong sparse partition is, like one level of this hierarchy. And here's some nice hierarchical clustering stuff for Raj and Kuba. So what is a strong sparse partition? Informally, the way I want you to think about it is it's like a partition of a vertex set into low diameter parts, where if you look at any ball that is sort of appropriately reasonable, that ball intersects a small number of those parts. So the picture you should have is like, here are all the vertices of my graph, or even metric if you like. And now I'm going to partition these into a bunch of sets, where each of those sets is such that the any pair of points within the same set is sort of nearby. And if I look at any ball which is reasonable, say like this red ball, it doesn't intersect too many of those sets. Namely, this like red ball intersects 3 of these sets. So more formally, what is a strong sparse partition? It's going to have this diameter parameter delta, and then these sparsity parameters alpha and tau. As I said, it's just a vertex partition of the original graph. What are the properties it satisfies? Well, first of all, it's like a low, strong diameter vertex partition. Namely, if you add back all of the edges from your original graph that have both endpoints incident to the same part, and you get a bunch of induced graphs like this, then each of those induced graphs should have diameter at most delta. So
Within the subgraph, right?
and yeah, so basically you can only move around staying inside of the part, and then you're supposed to have low diameter. Okay, now the second point here is something about this ball intersection. Namely, if you look at any vertex, and you look at a ball of radius about delta centered at that vertex, not exactly delta, actually delta shrunken down by this alpha factor, so you should think of alpha as larger than 1, then that ball is going to intersect at most tau many parts. So the picture here is like, I add back all of the edges of my graph, like this is the whole graph, and now if I look at any vertex V, and I look at all of the other vertices it can reach within distance delta divided by alpha, there should be at most tau of those, so like not too many. So again, this red ball doesn't intersect too many of the blue parts. Okay, so I claim that if you give me a delta and I'm in a path, let's say, then I can always compute a strong sparse partition with like constant alpha and tau. So here's my path. Does anyone want to tell me how to compute such a thing?
Blocks of delta.
Yeah. So if I just take sort of like contiguous subpaths where each of these things has length delta, and now I think of a ball of radius, say, delta over 2 or so, that ball can only intersect, in this case, like 2 of the blue parts. And you can imagine shifting this ball anywhere around the line. Okay, so there's kind of like this general trend in low diameter vertex partitions like this, where if you think about a path, you can get constant parameters, and then when you go to general graphs, you pick up a log n. And that's actually true for these strong sparse partitions. Namely, if I give you any delta, then I can sort of compute a strong sparse partition with alpha and tau of log n. So now, basically, if I take any of my delta balls, shrink them down by a log n, then they'll intersect at most log n of the original parts. Questions about that?
You're citing the MPX paper. Is it because like the basic algorithm can utilize?
Yeah, so it's kind of like a funny reanalysis of MPX in Arnold's ICAL paper from 2020. But it's basically you run the MPX algorithm. And one thing which is nice about this is, I guess, if you care, you can also efficiently parallelize algorithms to compute these things. Okay, so where does this leave us? Well, that was like one level of this hierarchy of strong sparse partitions. So now I have to tell you what one of these hierarchies are. So informally, the way I want you to think about these hierarchies is it's just a series of coarser and coarser strong sparse partitions. So I start off with my graph. At the bottom level of this hierarchy, I have a strong sparse partition with very small diameters. So think every vertex is in its own part. And then I take some coarsening of that. So now the diameter gets larger, and the like next level, namely these green parts, or the green partition, sort of are formed by swallowing up some number of parts from the level below, and so on and so forth, until I end with the trivial partition that puts everything in a single part. Okay. So more formally, what actually is this? So we'll again have these alpha and tau sparsity parameters, and now we'll have this gamma parameter that dictates how quickly the diameter grows from one level to the next in our hierarchy multiplicatively. So in particular, one of these hierarchies is just a series of vertex partitions. The first of those vertex partitions is just the singleton partition, like it puts every vertex in its own part. The last of those puts all of the vertices in a single part. Each of these partitions are supposed to be one of these strong sparse partitions, namely a strong sparse partition with these sparsity parameters alpha and tau, which are kind of inherited from the hierarchy, and now their diameter is gamma to the I. So again, as you go up one level in this hierarchy, your diameter will increase by a multiplicative gamma. And each of these is supposed to coarsen the last. So the way that you form the ith, like a part in the ith level of the hierarchy, is you take a bunch of parts from the I-1 level of the hierarchy and you sort of union them together. Now, I mean, one thing I'll note is if you didn't have this coarsening property, you could just sort of like independently compute each level of this hierarchy by calling this algorithm that I already described. Okay, so here's a question. Again, I got many questions for you all, which is, and I don't think this was in the talk that you were at, Raj, but which is, I claim that if gamma is huge, like think gamma is like larger than the maximum distance between any two vertices, then computing one of these hierarchies is trivial. And in particular, you should think of like gamma as, again, something that we want to be small for this reason.
Then you need just one, right?
One, or, well, I've already kind of enforced that.
Well, I mean,
bottom level.
non-trivial, right?
Yeah, well, okay. So then, I mean, basically, you can get away with like a two-level hierarchy where the bottom level is just everyone in their own part, and then you'll have to increase the diameter of this thing by a huge amount. And alpha and tau will be like, I don't know, 1 or maybe 2, depending on like some radius versus diameter thing. So yeah, so we should think of gamma as something we want to be small. Now, what's known about these hierarchies? Well, this previous paper from Fox about 10 years ago showed that if you can compute one of these hierarchies with alpha and tau parameters and gamma parameters, then basically those parameters up to like polynomial terms just multiply together with another log n and give you universal Steiner trees of that quality. Okay, so this previous paper basically said if I start with one of these hierarchies, then I can produce a universal Steiner tree. Now, what can we do with that? Well, they said, oh, actually, you can compute these hierarchies with reasonable parameterizations, namely 2 to the root log n parameterization. And basically, plugging that into this connection allows them to get 2 to the root log n approximate universal Steiner trees. Now, what did we do? Well, but we improved the quality of those hierarchies to be polylogarithmic. And so we're able to get alpha and tau equal to log n quality hierarchies with gamma of log squared. And notice that these alpha and tau parameters now match what is known for a single level of this hierarchy. And in fact, that's known to be tight for a single level of the hierarchy. So the only slack here, like the thing that could possibly be improved, is gamma of log squared. Okay.
Is the universal Steiner tree the only application? Because it feels like it's a more general tool.
Yeah. So as far as I know, it is. I mean, there are lots of applications of strong sparse partitions, but strong sparse partition hierarchies, this is the only application I know. But you'll see on my concluding slide, future work. I mean, I think there's like a nice question there. I don't know what other applications you can get, but so just returning to this, we like plug these strong sparse partition hierarchies into this connection, and then we end up with our polylogarithmic universal Steiner trees. Okay, so that's all about this first connection. And now I want to tell you all how to compute one of these strong sparse partition hierarchies with polylogarithmic bounds. Well, I'm cruising here. So, I mean, here's like a very basic idea. I'm just going to do something agglomerative. So I'm going to start off with like a very fine partition. Then I'm going to like fuse together some of these parts to get my next partition. I'll fuse together some of these parts to get my next partition. Yeah, it looks familiar.
Oh, you have to do this, right?
Well, you could also imagine doing something top down.
Oh, I see.
You could also imagine sort of like doing something independently at every layer, and then sort of like making, I don't know, subsequent layers respect each other and coarsen each other. Like it doesn't necessarily have to look like this. But this is what we're going to do. Okay. So how do we go from like one of these strong sparse partitions to the next? Well, in particular, how do we compute like the ith strongest partition from the I-1? So think we have like this blue partition on the right. Basically, here's like the idea. First, we're just going to add a bunch of degree 1 vertices to our graph that satisfy some kind of like nice net properties. And I'll describe more what I mean by that later, but I'll call these like dangling nets. So sort of I add these new vertices to the graph that are kind of like hanging off or like dangling off of my graph via new edges. And then what I'm going to do is I'm going to somehow coarsen this original partition that I started with some sort of subroutine that I'll call cluster aggregation, which guarantees that I end up with exactly one net vertex in the new coarsened partition. So in particular, after I coarsen, the picture will look something like this. Like I have a bunch of green coarsened parts, and each of these green coarsened parts kind of uniquely corresponds to one of these new net vertices that I added. So these net vertices are sort of guiding the coarsening. Okay. There's like a very sketchy idea of how to do this. Now I'm going to give a very sketchy proof of why this works. So here's like the main non-trivial thing we want to show is that like if you think about one of these balls of appropriate size, then it doesn't intersect that many parts. So the proof is going to go something like the following. I'm going to think about one of these balls. I don't want to intersect too many of the green parts of like appropriate diameter. And now I'm just going to appeal to first a property of this like cluster aggregation routine. Namely, this cluster aggregation routine will guarantee that if you look at any vertex inside of this ball, you know, it'll get sort of aggregated to one of these net vertices, like to something that's relatively, it'll be aggregated to one of these net vertices, and in particular, cluster aggregation will guarantee that it's aggregated to a nearby net vertex. So if you look at, in particular, if you look at any vertex in this ball, it'll end up in the cluster of like one of these 3 net vertices inside this sort of like radius of nearbyness. And then the dangling net is just going to guarantee to us that there are not that many nearby net vertices. So in this case, there are only sort of 3 quote unquote nearby net vertices. And what this means is that after you cluster, like after you like coarsen your clustering, the only coarsen clusters that can sort of eat into this ball are those that have a corresponding net vertex that lies in this nearby ball, but there aren't that many of them. In this case, there are at most 3, and so there are only at most 3 clusters that eat into this ball and therefore intersect this ball. So like if you remember nothing else from this talk, like this is really, like this is the entire idea of the paper, and everything past this is sort of just like formalizing this idea. So I'm gonna like hang on this for a moment and let it digest, / answer any questions that anyone might have. Hopefully this is like clear. It's not like a galaxy brain argument. Okay, I'm gonna move on. So I want to describe how to do this, and in order to do that, I have to actually tell you what this like cluster aggregation dangling net objects and subroutines are. So let me first start with cluster aggregation. So what is cluster aggregation? Well, we're going to imagine that we start with some vertex partition of our graph, think this blue partition, and we're going to imagine that we have a bunch of vertices designated net vertices, think the vertices that come from these dangling nets, where we have at most 1 net vertex in each of our parts. Okay, so here, you know, there's either 0 or 1 net vertex in each of these blue parts. Okay, now all we want to do is we want to coarsen this so that we end up with exactly 1 net vertex in each of the coarsened parts. So a feasible solution might look something like this green thing, where now basically each of these green parts is exactly 1 net vertex. And this is kind of like the property I described in the preceding slide. Now, what are we actually, like what's the objective here? Well, what we'd like to do is we'd like to coarsen this partition in such a way that if you like look at a vertex and you look at its nearest net vertex, and you look at its nearest net vertex within its coarsened part, those 2 things should be relatively close. So in particular, if you look at, say, this vertex, maybe its nearest net vertex is the one down below right here. Like if these are all unit weight edges, it only has to go 1 edge to find a net vertex. But then if it wants to go to its nearest net vertex in the coarsened part, it has to go to that net vertex. We just want this like red distance to be not that much larger than this green distance. Okay. So let me do this formally now. There'll be like more notation. So what is an instance of cluster aggregation? I give you a graph. I give you a subset of vertices that I'll call net vertices and some vertex partition where this vertex partition has diameter delta, subject to the constraint that if I look at any one of the parts in this partition, you should have at most 1 net vertex. Okay, so in particular, if you look at the diameter of any one of these blue parts, it's at most delta. And now, what is a good quality solution? I'll say that A solution is a coarsening of the blue partition, and it has beta distortion if basically you have to go like beta-ish farther additively to get to a net vertex. In particular, you want to coarsen the partition so that you have exactly one net vertex in each of the coarsened parts. And now if you look at the distance that a vertex has to go to get to its nearest net vertex inside of its coarsened part. So if I coarsen my part like this, then this vertex has to go there. That shouldn't be that much more than its distance to get to some net vertex, like just any net vertex. Namely, you should pay at most an additive beta times delta. So sort of the units of distortion here that we're measuring things in are the diameter of these blue parts. Okay. And in particular, like if you look at this vertex here, it originally could go to this net vertex below, but now it has to go to this other net vertex. And I've set this up so that these are all unit weight edges. The diameter of each of these blue parts is 1. So basically, originally you could go 1 to get to a net vertex. Now you have to go 3, and delta is 1. So your distortion here, beta is 2, at least for this vertex. And you can verify that for every other vertex, it's no worse. And this is like a distortion minimization problem. So our goal is just to minimize beta for this problem. Okay, so this is this cluster aggregation problem. And kind of the interesting thing here that's happening is we're measuring distortion additively. And like usually when we talk about distortion, we think of something that should be at least 1, like it shouldn't be something less than 1. And I claim that's true for this problem. Namely, there's like a simple-ish example that demonstrates that distortion is always at least 1 here. I'll just say the answer to this myself. So here's just like a very simple example just to help us like get a handle on this problem. Namely, I have 3 parts, only 2 of them have net vertices in them. And now this part in the middle has to be aggregated to either the left or the right. So up to symmetry, let's say it goes this way. And now if you had this vertex, if you think about this vertex on the right, originally you could just go 1 edge to get to the net vertex on the right. But now it has to first travel across this delta diameter thing and then go its 1 distance to the net on the left. So there are simple examples that sort of just existentially show that distortion is at least 1. Okay. So originally you could do that, but now you have to do that. Now, what did we show for this problem? Well, basically you can solve this problem with distortion at most log n. And it's some sort of like, I don't know, like nice symmetric tie-breaking argument. There's some like cute probabilistic arguments to do this. But basically you can solve with log n, and I guess we have some unpublished super constant lower bound. So like in some sense you shouldn't do better. Okay. So returning back to our like sort of algorithm roadmap for how to go from one level of the hierarchy to the next. I told you all about this cluster aggregation problem, and that cluster aggregation sort of took as input some net from this like dangling nets subroutine. So now I have to tell you about these like dangling nets. And I just told you how to do cluster aggregation with distortion of log n. So let me talk about these dangling nets. And I think these are kind of, and it's kind of like a funny object and interesting. So informally, like what are these dangling nets? Well, I'm gonna like start with some graph, and then I'm gonna add a bunch of new degree 1 vertices to the graph so that, well, first of all, every vertex should be close to a net vertex. So like if I look at this vertex V, the distance it has to go until it finds one of these net vertices should not be that large. And second, there shouldn't be like that many nearby net vertices. So if I go like a bit further than I had to go to find one of these net vertices, then I shouldn't find that many other net vertices. So in this case, I find a total of 3 net vertices. If I look a little bit further, then I had to look until I found 1 net vertex. So let me do that more formally. See the return of these alpha and tau sparsity parameters. So a delta, like if we imagine that we're given some diameter delta, then a delta covering alpha tau sparse dangling net is just some like subset of new vertices. I'm using this notation to say that these were not vertices in the original graph, where those vertices are sort of matched to vertices in the original graph. So this is just a way of saying it's a bunch of new degree 1 vertices, and each of those edges doesn't necessarily have to have the same length or weight. So here's sort of like what a dangling net looks like that satisfies the following property for every vertex. So first of all, every vertex should be close to a net vertex. So if you look at this vertex V, the total distance it has to travel in the graph until it finds some net vertex is at most delta. And then you don't want like too many nearby net vertices. And the notion of like too many and nearby is a little bit, or really the notion of nearby here is interesting. So basically, you want what I'll call additive sparsity, where if you look at the number of net vertices whose distance from this vertex V is at most the distance of the original, like the vertex to its nearest net vertex, plus some delta over alpha, should be at most tau. So the picture here is like, you look at this vertex V, it has to travel some distance until it finds some net vertex. And then if it just explored a little bit further, like an extra delta divided by alpha, it would find not that many new net vertices, at most tau. In this case, it finds a total of 3. So maybe tau is like 3 here. So this kind of, the interesting notion of nearbyness here is like, you're measuring nearby as a function of how close you are to your nearest net vertex, not just something absolute. Like I'm not saying the number of things within delta plus delta divided by alpha is at most tau. I'm saying go until you find somebody and then go a little bit further. And that total distance might be much less than delta plus delta divided by alpha. Okay. Any questions about that? Okay, so if you don't have questions for me, I have questions for you, which is, why does this net have to dangle? Namely, like, there's something I think something very interesting happening in this definition. And if you've like thought about, I don't know, nets before and computational geometry or something, usually what we're used to is a definition that looks more like the following. Namely, we want our net to be a subset of the vertices. So you might imagine, like you might wonder, why can't I just get a similar thing where I'm just looking for a subset of vertices of my original graph that basically guarantee that everybody's close to something and nobody's too close to too many things.
What is the distance of a net vertex to its neighbor? Is it something that you're gonna tweak, or is it's not 0, right?
The distance of a net, in like the previous definition, you mean?
Yes.
It's something that I'm kind of allowed to tweak. And I mean, I want to make sure that every vertex is within delta from some net vertex, but that initial thing is, in fact, it could be anything you want, really. I mean,
So I guess you probably need this for adaptive sparsity to be possible, right? Or like to be
or additive sparsity.
sorry, additive sparsity.
Yes. Well, okay. Well, yeah, you're preempting my example here. So
Ask a question.
yeah, I know. Yeah. Okay. Well, I asked a question and you correctly answered it, and now let me expound upon your answer. So like the point here is that if I allowed for this net to be or if I force this net to be a subset of vertices, I claim that you can't achieve tau of like polylogarithmic quality. Namely, it'll be like polynomial. So here's just like a very simple example. I'm going to take a star with like fan out root n, and everyone is going to have length delta. And then I'll just hang a star off of each of those leaves, again, of fan out root n, where every edge has length delta. Okay. And now if you're like trying to enforce this definition and you're over here and you said like, well, suppose I don't choose one of these nodes in like level 1, then that means all of the leaves under it have to be chosen just because each of these leaves is within delta of only that node or themselves, right? So if I don't choose this vertex, then I have to choose all of its children. Okay, but then of course I can sort of like look at the ball center to that vertex. Now I found root n net vertices. So you might say like, okay, definitely better choose that vertex, and symmetrically I should do the same thing for all of those. Ooh, I think I pressed the wrong button. Symmetrically I should do the same for all of those. But now I can just look at the ball centered at the root. And again, I've discovered root n vertices. And in fact, I think you can actually prove that you can always achieve as an upper bound root n for such an object. So in some sense, this is tight. And recall that our whole goal here is like something polylogarithmic, so we probably don't want our definitions to be sort of requiring a root n. So returning to the original definition, in this counterexample, I actually claim that computing a good dangling net in the way that I described it, given some delta, is trivial on this example. How?
You add edges of like delta over constant, right?
Yeah, or let's even just say, let me do something like even more head empty than that and just add edges of length delta to everybody. And so now everyone's definitely within delta. And if they travel a bit further, namely they can travel even an additional delta after they first find a net vertex, they won't find any other net vertices. Okay, so all of a sudden, because I've allowed you to, in some sense, pull the distance of these net vertices away from the rest of your graph, you can somehow construct like much nicer sparsity guarantees for that. Okay, so what can you show about such dangling nets? Well, you can show that you can always compute these dangling nets with quality log n. And in some sense, it's just MPX, but you have to be very careful because you really care about sort of like strong diameter guarantees. And there's a sort of an analysis also in this paper of Arnold that sort of does this, but not exactly. So it's sort of like, I don't know, you can like half attribute it to an existing paper, but basically you can, what this means is that you can hang vertices off of a graph so that every vertex is within delta and sort of the number of vertices, the number of net vertices within a little bit more, like namely delta over log n of your closest net vertex is at most log n. And if you're familiar with the analysis of MPX, it should hopefully make sense to you why this is possible.
So the construction is randomized.
Yes. But I think there are probably standard de-randomization techniques that would work to de-randomize it.
So the construction is like you're giving every vertex a timer, and then the first.
Yeah, and then the weight of the edge is basically the timer. But the analysis is not, I mean, you have to do more than sort of say the original analysis of MPX. But the intuition is sort of like the first time you're visited by somebody, they're sort of like with constant probability, they sort of swallow you up and you'll never be like visited by somebody again. So if you're visited like log n times, something like that. But okay. And the technique is kind of what we've been talking about, is sort of like this exponential clocks idea from MPX. But I think this is kind of an interesting, I don't know, it's sort of like a result from parallel algorithms telling you something about just sort of the existence of some kind of graph structure. So let me move on. Returning to our picture, we're trying to construct one of these hierarchies. I told you all how to get logarithmic quality, like aggregation of clusters, and now I just told you how to get logarithmic quality dangling nets. And now all we have to do is just smash these two things together to get our hierarchies. So let me try and describe that in a bit more formality. Okay, so again, the picture you should have in your head is like, well, what we'd like to do is we'd like to say, like, look at one of these balls that we don't want to intersect too many things, look at the number of things that are nearby to that ball, and there should be a small number, or the number of net vertices nearby that ball. All the things in that ball will get aggregated to a net vertex, and there aren't that many nearby things. Now we've seen sort of like the formal sense in which cluster aggregation will send things to like nearby net vertices, and the formal sense in which dangling nets ensure that there aren't that many nearby net vertices. So, okay, now is when I like try to say as much as the proof as I think the audience will tolerate. Let me just like state the algorithm because it's like pretty simple now that we have all the appropriate definitions. So if we want to compute the ith level of our hierarchy from the i-1th level of our hierarchy, where we imagine that we've sort of correctly computed the i-1th level of the hierarchy such that it has diameter gamma to the i-1. And for the purpose of this proof, I'm just going to set gamma to be alpha times beta. So alpha is going to be the sparsity parameter from the dangling nets, like how much you're shrinking down the exploration after you find your nearest net vertex. Beta is again going to just be the distortion quality of cluster aggregation. So here's the picture. This is like the i-1 level of the hierarchy. And now all I'm going to do is just compute a dangling net with appropriate parameters. Namely, I'll compute it. Suppose I can compute it with alpha and tau, which you should think of like as log n sparsity. And I'll set gamma to be essentially gamma to the I. I mean, I'm hiding the constants here, but it'll be like alpha times beta, which again is like gamma times gamma to the i-1. So this is essentially gamma to the I up to constants. And then, so I compute my dangling net, and then I literally just run cluster aggregation. So I let the next level of the hierarchy just be the result of cluster aggregation on this partition using the net vertices that I computed from this dangling net. And that'll give me back some coarsening, and I'll just call that the next level of my hierarchy. Okay, that's the entire algorithm to compute these hierarchies. Any questions? So there's like there are two non-trivial things we have to guarantee. One, we have to make sure that the diameter of these green parts is not that large, namely it should be at most gamma to the I. The second is the ball intersection property, which is the more interesting and harder to show one. Let me start with just the diameter analysis, which is like pretty quick and hopefully not painful, and just requires that you remember the definition of these two primitives. So if you remember, I got moved. These like dangling nets guaranteed that every vertex is at most delta from, okay, goodbye, Goran. I'll talk to you soon. these dangling nets guarantee that every vertex was at most delta from some net vertex. So if I look at this vertex, then its distance from its nearest net vertex is at most delta. But of course, cluster aggregation doesn't send you necessarily to your nearest net vertex, it sends you to some other net vertex, which is not that much further than your nearest net vertex, okay? In particular, cluster aggregation will guarantee that the net vertex to which this gets assigned is not much more than delta. If you remember the guarantees, it's like delta plus the distortion beta times the diameter of these like blue parts. The diameter of the blue parts is gamma to the I-1. So in particular, the distance that this vertex has to go to get to its aggregated cluster is like delta plus beta to the gamma to the I-1, where again, this is the diameter of the blue partition, this is the distortion from cluster aggregation, and this whole thing is because these distortion guarantees are additive. And now just because of how I've chosen these parameters, like this whole thing is up to constants just gamma to the I/2, okay? So the point here is just that this vertex, instead of going to its nearest portal, got sent to this other portal, but because of how I chose the parameters, its distance to its nearest portal is gamma to the I/2. Now, just by triangle inequality, this means that any vertex in this green cluster pairwise are within gamma to the I. Okay, that's the diameter analysis. I don't know, what's the level of interest in the sparsity analysis? I kind of want to just like put it up. So like it's not that complicated. I only have to shrink the font down to this size. But this is like really genuinely like the entire paper sort of fit into, yeah, it's like 24.4 font. It's not that small. Maybe, I don't know. Yeah, I'll by vote.
You got 10 minutes, so go.
Yeah, I know we have 10 minutes. Okay, I'll just like say it. And even if it doesn't make sense, I guess I just want to impress on you all the fact that this is like a simple enough analysis that I can say the whole thing in like 3 minutes. And you won't see me use anything other than the definitions of the objects that I've already introduced and like triangle inequality. Okay. Let's see how this goes. So like the sparsity analysis, right, is trying to say that if you look at a ball of appropriate radius, it shouldn't intersect that many things. Okay. Now, appropriate radius for us is, again, gamma to the I divided by alpha. If you remember, it's kind of the guarantees that we're trying to like ensure. And just by our choice of gamma being essentially alpha times beta, gamma to the I divided by alpha is just like beta times gamma to the I-1. So I'm just, yeah.
Just future, I think when we're going down to 20-point font, we should keep it all in black.
Yeah, maybe you're, well, normally the screen is bigger and the people are closer. But
I can read it though. I can read it.
Okay.
I have good vision.
Okay. Yeah. But I mean, the point is that like, we're thinking about some vertex, we're thinking about the ball around that vertex that we don't want to intersect too many of these green parts. That thing just has diameter beta times gamma to the I-1. This is just by how we choose our parameters. Okay, and then all we do is we say like, well, that should mean that every vertex in this ball is like pretty close to a net vertex. Namely, V has some distance to its nearest net vertex. Any other vertex in this red ball can always go to V and then go to V's nearest net vertex, okay? So that means that if you look at any U here, and you look at its nearest net vertex, say it's like that one, well, this distance should be at most the distance of V to its nearest net vertex plus essentially the radius of that ball. I mean, if you think about how shortest path stuff works, it's really twice the radius of that ball, which is, as I just said, beta times gamma to the I-1 up to constants, okay? So all I've said so far is just like everybody in this red ball is essentially as close to a net vertex as the center of the red ball that we don't want to intersect too many parts, namely V. Does that like make sense? Even if the exact parameters don't make sense, but like, yeah, okay. It's like some head bopping. Well, the pain will be over soon. I feel like I need at least like one slide that makes this look like real research. So what do we know? Well, U didn't get to go to its nearest net vertex. Cluster aggregation aggregated U to some other net vertex, but one which is like pretty close. Namely, you should pay at most the distortion factor, beta, times the diameter of each of these like blue parts, which if you remember is gamma to the I-1. So I'm just kind of like saying parameters here, but the point here is that if you measure U's distance to its nearest net vertex, that should be, or sorry, use distance to the net vertex that it gets aggregated to. That should be at most its distance to its nearest net vertex plus another beta times gamma to the I-1. So the whole thing is just this distance plus another beta times gamma to the I-1, which gets swallowed into the O there. And the actual paper has the actual constants, and, it's not so fast and loose. But basically, the distance of any vertex in this ball that we care about to the portal that it gets aggregated to is small. Small as a function of what? Well, small as a function of V's, the center of this ball's distance to its nearest net vertex. And that's like the interesting thing, okay? And what does this mean? Well, it tells us that like if some vertex in this red ball, in this case U, is assigned to some net vertex, then the distance of that net vertex to V is small. Namely, V can first traverse this ball and then traverse to that net vertex. This ball has radius, again, I'm just saying the parameters, but like beta times gamma to the I-1. And in particular, what that means is that the entire distance from V to this net vertex is essentially the distance of V to its nearest net vertex, plus some extra like beta times gamma to the I-1. Okay, so the little magic trick I'm going to play now is I'm going to say like, well, any vertex in this ball which gets aggregated to a portal will get aggregated to a portal which satisfies the property that that portal is close to V. So I can sort of like, as I was saying, draw this like zone of nearbyness around this vertex V and just say any portal that sort of chews into this ball, namely any portal, or sorry, I keep saying portal, but I mean net vertex. Any net vertex whose cluster chews into this ball, namely that has any net vertex which has a vertex in this ball aggregated to its cluster, must be within this radius of the distance of V to its nearest net vertex plus another delta divided by alpha. And this is, again, just kind of how I chose the parameters. But now all we have to do is say like, well, this is exactly the radius around which we know that there are not that many net vertices. Namely, these dangling nets guarantee that the number of net vertices in this zone of nearbyness is at most tau, which tells us there are most tau parts that intersect that ball. Okay, the pain is over. You can forget everything I said. I mean, I just want to sort of emphasize though how like it's like 4 bullet points is really like the main contribution of this entire paper. It's something you could understand on your own time in probably like 20 minutes. It's nothing intergalactic. And the algorithms themselves are even like quite simple too. So if that didn't make any sense, this is really the slide I want you to remember, which is again, like all we're going to do is we like look at the balls that we don't want to intersect too many things. We say that basically any vertex in that ball can only get aggregated to some net vertex, which is nearby, like in this zone of nearbyness, but there aren't that many things which are nearby. And the previous slide was just me formalizing that argument. Okay, so that's like basically my talk. I'm going to skip this. I mean, you can formalize that argument in a way that tells you like, well, if you can always compute good dangling nets and good cluster aggregation, then you can compute good hierarchies. This is just by applying sort of this argument I gave for each level of the hierarchy. And then you just sort of push through the fact that we have good dangling nets with logarithmic quality and cluster aggregation with logarithmic quality. And then out pops hierarchies with polylogarithmic quality. But let me skip this. So this is like the main roadmap, if this is how it all fits together. I spent most of the talk just sort of describing how to get these strong, what all these things are, and then how sort of dangling nets and cluster aggregation give you these strong Sparse partition hierarchies. And let me just like quickly wrap up. So this was a talk ostensibly about universal Steiner trees, but really about strong Sparse partition hierarchies. So a universal Steiner tree, again, is just sort of one spanning tree that approximates, I did that wrong. It's that one spanning tree that approximates all Steiner trees well. We gave the first polylogarithmic approximate universal Steiner trees. In some sense, this is like optimal up to what exactly the polylogarithm is. The way we did that is by giving polylogarithmic quality strong Sparse partition hierarchies. And we use these idea of dangling nets and cluster aggregation. And there are some like nice open questions here. So like the first and most obvious one is, can you close this gap between this like log n lower bound, log to the 7 upper bound? Another thing that's natural to study is sort of these kinds of objects for special graph families, say like graph families that you might reasonably expect to encounter in practice. And the last thing here, I guess, goes back to like Kuba's question at the beginning, which is like, I think in some sense, like universal Steiner trees and strong Sparse partition hierarchies are just like graph objects that have no business existing. Like it's kind of bizarre that you can find one spanning tree that's a good approximation for all instances of Steiner tree. And I think for that reason, there ought to be more applications of these things, but I don't know of any. So with that, I'm going to finish my talk and thank you for your attention. Cool. Yeah. Any questions? Are we going to get kicked out of here in 1 minute?
But
Well, left
Just-
on the dot.
yeah,
Oh, there's a raised hand. Yeah. Do I call on them somehow? Or...
yeah,
Yeah,
Oh,
please.
so question. So when you're constructing these dangling nets, you were saying it's important that they're dangling.
Mhm.
So basically the distance between the dangling node and the sort of actual node in the graph, is that sort of one fixed distance for all the different dangling things? Or
Yeah, so
you choose
very
all of those
important.
independently?
Yeah. So very importantly, it's not a single fixed distance. It's different for every node. And you can I mean, it's not too hard to construct examples where you actually require that it's different for every node. And sort of intuitively, you'll have like a small number with very large distances and like a large number with very small distances to sort of hit every scale of the graph.
Yeah, I was just curious because I mean they're kind of slack variables to make the things work out. And so I was wondering if there's just one variable you use everywhere or
Yeah, no.
Sorry, we're getting kicked out.
Okay, we're getting kicked out. Yeah. Thank you all.